Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon, everyone. I think maybe most people here have studied probabilistic combinatorics from the wonderful book by Alon and Spencer, and now we have Joel himself to tell us about the first order world of Galton-Watson trees.
Okay, thank you, Yuval. It's a pleasure to be back in Redmond. I want to talk about a well-studied subject, Galton-Watson trees, but from a somewhat different vantage point. So let me begin, though, by saying what Galton-Watson trees are. So this is a model for a rooted tree. Initially, it was a demographic model for the aristocracy of England, which Galton and Watson were afraid was dying out. Fortunately, they were correct. But so here's the, but they came up with a good mathematical model. So here's the model. You start out with a single node called the root, and then the root has children, and the number of children is given, at least this is what we'll look at, is given by a Poisson distribution with mean lambda. Okay? You can actually look at it with other distributions, but we want to look at the Poisson distribution. And then, so maybe the first one has 3 children, and then you go down, and then this one has maybe 1 child, and this one maybe has 0 children. Each node, the number of children independently, has the same distribution, the Poisson with mean lambda. So lambda will be the critical parameter here, and maybe this one dies, and well, maybe this one dies. So maybe the whole tree just dies after a while, but it's possible that it can go on forever as well. In fact, that's one of the key things to look at. In terms of probability theory, the way I'm going to describe it is to have an infinite sequence of IID Poisson lambda variables, and then just to say that the root node, the first node if you like, has x1 children, and then the next node has x2 children, and the next node has x3 children. And the underlying probability space is this infinite sequence, though I like to use the phrase fictitious continuation here. Because it's quite possible that the process will stop as it did in this case. In particular, if x1 equals 0, the process stops. So the underlying probability space is this countable sequence of IID Poisson lambda random variables that determines the tree. But if the tree does stop in finite time, then the rest of them simply aren't used. But it's very handy to look at it that way. So this is called the Galton-Watson tree. And now if you have a property A of trees, you would have a probability that'll be a function of lambda, which is the probability that the property A holds as a function of lambda. And this is what we want to look at. How can things depend on lambda? So I want to start with 2 examples that are somewhat similar, but in a critical way, from my point of view, are quite different. The first one I'll just write it schematically. What I mean by this is there exists a node that has exactly one child, and that child has exactly one child. Okay, so all right, I mean, I could have given you some other one, but this is one that we'll look at, okay? And if we want to analyze that, very nice exercise, but I'll show you how to do it. We can define it by, we can analyze it by looking at three states. So the state of a node will be, see, one thing with rooted trees is that each node defines a rooted tree, that node and all of its descendants. And indeed, those things have the same distribution as the original Galton-Watson property. So we'll call a node green if the answer is yes, that is, inside the tree generated by V, there is a node, possibly V itself, that has exactly one child, which has exactly one child. Then we'll call, we're going to have three states. We'll call a node blue if it's not green but it has precisely one child. It's sort of part way toward getting this, as we'll see. And we'll call a node red if else. So to analyze this, we'll say that a node is green if in the tree generated by it there is such a node, possibly the node itself, that has one child, exactly one child with exactly one child. It's blue if it's not green, but it has exactly one child, and otherwise it's red. And then they will have probabilities, let's call them X, Y, and Z. But they're really only two variables because they add up to one, the probabilities. All right. Now the thing is that the state of a vertex is determined by the states of its children. So how does that work? Well, if you have, I'll just write it schematically, if any of the children are green, then the parent is green. Because for a node to be green, it means inside it there's this special node, child, grandchild. Okay, so then all of its parent will also have this. But it can also be green let's see, or suppose the node has only one child, exactly one child, but that child is blue. That means that it had exactly one child, and then that means that you're green. Sorry, I'm getting my colors messed up. Okay. That also means that you're green. And on the other hand, for becoming blue, if you have a node and it has exactly one child, and that child is red, then you become blue because you had exactly one child, but that child was red, so it didn't have anything inside it. So you are blue, and everything else is red. Everything else is red. So the state of a node is determined by the states of its children. Okay, and these are the rules for them. Now, because of this, we can give some equations for x, y, and z. So maybe I should write them down because I'll... So what is the probability that you're green? Well, either you have a green child. Now, the Poisson is particularly nice. Beautiful thing about a Poisson is if you have a Poisson, if you're going to have Poisson lambda children, and each one is a boy with probability 0.4 and girl with probability 0.6, then you're going to have Poisson 0.4 lambda boys and Poisson 0.6 lambda girls, and those are independent numbers. This is one of the beautiful properties of the Poisson distribution. So here, what we can think of is if we take a node, it's going to have Poisson lambda x green children, Poisson lambda y blue children, and Poisson lambda z red children. So what's the probability that it's going to be green? Well, if it has any green child, it's green. The chance that it has no green child is e to the minus lambda x. So we get 1 minus e to the minus lambda x. But we also might have a single child, which is blue, and that is, one can do the computation, it's lambda e to the minus lambda times y. Because you'd have to have exactly one child, which is lambda e to the minus lambda, and then given that, that child would have to be blue, which is y. On the other hand, what is the probability that you're going to be green? You have to have exactly one child, blue, you have to have exactly one child, which is red, so it's lambda e to the minus lambda z. And I don't have to put in the third one because these are distributions. Their sum has to add up to 1. Well, this can be solved implicitly, okay? There's not an explicit solution, but you know, there's a solution, and here's lambda, and I don't know. Actually, I think it goes up. I'm pretty sure it keeps going up, but that's not. It's some kind of smooth solution. Okay. As a function of lambda. This is x. Yeah. This is. But I mean, I could do it for y or z as well. But see, x is the event that we want. Okay. But you know, equally well could be done for so x is a function of lambda is some smooth function. Okay. Well, that's nice. All right. Now, in contrast, let's look at the very basic thing that poor Galton and Watson were so worried about, which was that the aristocratic families would disappear. So what is the, let's look at the event that the tree goes on forever, that the tree is infinite. So the second property is that t is infinite. And now we can do a similar analysis where there are just two states, yes and no. Either V generates an infinite tree or it doesn't. It generates a finite tree. Again, there's really only one variable because these are distributions. And again, what we have is that if any of the children are green, then the node is green. If any of the children, so Adam had Cain and Abel. Abel, unfortunately, didn't work out too well, thanks to Cain. But maybe the tree is infinite. We don't. Anyway, so all you need is one child that's infinite, and then and then you're infinite. Okay, so well, this is good, and this is very classical. And then what is the probability? I always write it down wrong, so let me try and get it. That x is the probability that there is at least one. So you have Poisson lambda x green points. So you need at least one green point, which means that you don't have 0 green points, which is 1 minus e to the minus lambda x. And if you've studied Galton-Watson trees, this will be familiar to you. This is the equation for survival. And when you graph it, two things happen that are different. The function is not smooth. Well, it's continuous, but it's not differentiable. When you solve the equation at lambda equals 1, for lambda less than 1, the solution is 0. For lambda greater than 1, there's a solution that does not have, so the right-hand derivative at lambda equals 1 is 2, and the left-hand derivative is 0. So it's not differentiable at the point lambda equals 0. So that's a big distinction from here, where this function has all of its derivatives equal. Secondly, there is a spurious solution, which caused all those 19th century English a lot of grief, because they thought there was a lot of thought that the spurious solution, they said, look at this equation. Answer, x equals 0. 0 equals 1 minus 1. There's a solution. There's a lot of confusion about that, at least according to Peter Jagers, who studied the history of this quite a bit. So actually, the equation here, for lambda less than 1, the only solution is 0. But for lambda greater than 1, there are two solutions. So you actually get two functions. The actual answer to the problem, probability that t is infinite, is given by this curve. But if you look at the equation, you get this solution as well. That's not the case over here. This system of equations has a unique solution. So there are 2 points on which these two examples differ. One is that here you get a system of equations, in this case one equation and one unknown, but the solution is not unique. Here it is unique, and when you look at the solution to the original problem, here you get something that's a smooth function, all of its derivatives exist, and here you have a function that's smooth except at lambda equals 1, but at lambda equals 1 it's not differentiable. And so the question is, what, if anything, is going on? So I want to restrict the kind of properties that I'll look at. So our objects are rooted trees, and I want to restrict myself in this talk to properties that I'll call recursive. In the sense, in what sense? There are two aspects of it. First of all, there is a finite state space sigma. And secondly, I want an integer k, fixed integer k greater than or equal to 1, and when I count things, I'm going to stop my counting at k. Everything that's k or more is counted the same. And now, something that these two things have in common is you can describe the property by making a finite number of states. Here 2 states, here 3 states, but it's important that it be a finite number. And that the state of a node is determined by the number of children in each state. And furthermore, that number, once it gets to k, it doesn't matter how much bigger it is. So here, k is, let's see, do I want it greater than or equal to, I think I want it greater than or equal to k minus 1. No, greater than, yeah. So here, if you have if you have 2 or more children, might be off by 1. If you have 2 or more children of a certain type, then it doesn't matter. It does matter whether you have 0 children or 1 child, but if you have 2 green children or 50, if you have 2 blue children or 57 blue children, it doesn't matter. Okay. And over here, actually the counting is either you have 0 or you have some. And so I'll require for a recursive property that the counting stops at some fixed point. Let me mention one other case, just briefly. Consider the property that inside the tree, you can start with the root node, and you can take an infinite full binary tree. That is, from that root node, you can take 2 children. Maybe it has more than 2 children. You can take 2 children, and each of those have 2 children. Then each of those 4 have 2 children. And then each of those 8 have 2 children, and it goes on forever. This refers to something in graph theory called the 2-core. There's been a lot of work on it. One can, again, do something like this. Again, it's yes or no. And if you have 2 green, so k becomes 2. So if you have 2 or more green children, then you're green. And again, one gets a recursive formula. And there something very odd happens. The solution is discontinuous. And some of you, if you're familiar with studies of the 2-core, it's based on this. What happens is there's a critical value, lambda 0, and up to lambda 0, the value, actually, strictly speaking, less than lambda 0, the value is 0, and then there's a discontinuous jump. And then the probability that you have this infinite 2-core jumps to, I forget what number, but it's a specific number that's bigger than 0. So a number of odd kind of things can happen. So my interest is recursive properties in general. Okay. But now I'm going to add some logic to the mix in terms of talking about the properties. And I want to look at what's called the first order language in terms of describing properties. So I know I'll be in Leiden next month, and then I'll have to go very slowly over the probability, and I'll go quickly here. Here, I think I'll just give you some idea of it. If you're familiar with it, all the better. So I want to look at statements. So how am I going to allow myself to describe statements? I'll allow the normal Boolean and, or, not, those kind of connectives. I'll have variable symbols x, y, z. I'll be able to talk about the root. That will be a constant symbol, the root r. I'll be able to say that x equals y as nodes, and I'll be able to say that x is the parent of y. Think of that as a binary relation. And I'll have quantification. I'll be able to say for all nodes v, or I'll be able to say there exists a node w. I know that's a little redundant, but so what we're allowing is for all v, or there exists a w, and we also have equality, parent, and the root, and the usual Boolean connectives. And properties have to be finitely describable by a finite sentence. So if I want to look at this sentence, I'd say there exists w, x, and y, such that w is the parent of x is the parent of y, and there does not exist a z such that, or put it this way, if, and for all z, what did I say, w, x, y, for all z, if w is the parent of z, then z equals x. So that says that it has exactly one child. And if x is the parent of z, then z equals y. Okay, so these are the kind of sentences you can make. What can't you say? Well, first of all, the sentences have to be finite. You can't say there exists an infinite string, x1, x2, x3, x4, x5, dot, dot, dot. There's no ellipses in this language. Each sentence is finite. And the key thing about first order is that the quantification is only over vertices. You're not allowed to say there exists a subset of the vertices that has a certain property. You're only allowed to say there exists a vertex that has property such and such. So there are a number of things you can say, and a lot of things you can't say. One can prove that there's no first order property that says that the tree is infinite. I mean, it doesn't look, I mean, if you try and do it, you'll fail, but that's actually a theorem that you can't do it. There's any first order property, it will not be that the tree is infinite. Okay. Now, so this is called the first order world, and it's been quite well studied. And whenever you have a sentence A, you have the quantifier depth. So you look at the sentence A, and you look at the degree of nesting of the quantifiers. So if you say for all x there exists a y, blah, 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 and for all z there exists a w, blah, 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 that's the quantifier depth is 2 because the z and the w aren't inside the x and the y. So it's a notion of nesting, and we can look at what we're going to do throughout is to fix we're going to look at statements with a given quantifier depth, A. Now, a priori, there are an infinite number of those statements. But it's one of the deep results in it's not that deep, but it's not immediate, that they're really only effectively, they're only a finite number of classes. They're only a finite number of classes. So we can say that T is equivalent to T prime, and I'll put the little k down as a subscript, but then I'm going to leave the k out. For if So these are both rooted trees. So our objects are these rooted trees. For the moment, forget about the probability. They're just the rooted trees. If they satisfy the same A with quantifier depth of A, let's say less than or equal to K. I mean, quantifier depth is less than K. You can always throw in a spurious one. That doesn't matter. Okay. And there are only a finite number of equivalence classes. Okay, so this I'm going to just take as a fact. I should mention, though, that the number of equivalence classes actually goes up like a tower function of K. So this is the theory section, right? Yeah, so it's okay. All right, so we'll let sigma is the set of equivalence classes. And now any first order statement A of quantifier depth K is just determined by which subset of sigma you are, and sigma is a finite set. Now, in these cases, and in many explicit cases, I can make use of a much smaller sigma. So here I use 2 states or 3 states. But in general, I'm going to have this finite state space sigma, which let me just denote it by 1 through m, the states. And we're going to let D be the set of distributions on sigma. So the set of x1 through xm, such that summation of xi is equal to 1, and all xj are greater than or equal to 0. So this is a nice compact set, basically an m-1 dimensional space, the m-1 dimensional hyperspace, hyperplane. But think of it as the set of distributions over sigma. And now, what we're interested in, instead of looking at the probability of A, let's look at this Poisson tree, which has this lambda in it, and we'll look at its distribution in terms of what state it's in. And if we can get that whole distribution, then for any particular property A, it's just going to be a finite sum of those things. So what we can say is that let's write solution of lambda to be the distribution of the state of this Galton-Watson tree. Okay? So given lambda, we have this probability. We create this random Poisson lambda, this random Galton-Watson tree. And then we look at what state it's in. It's in one of a finite number of states. So what are the probabilities for each of them? Well, whatever they are, that's going to be our goal. And indeed, over here we had only 3 states, x, y, z, and we saw that they satisfied this equation, this system of equations. Well, this will now work. Almost left out a critical point. state that's a recursive function. Okay. Well, here I define recursive property, but I can also define a recursive function. So the value is which state you're in. It's the same thing. So I claim that in fact, the k is the same k of the quantifier depth. So this is a statement from logic, which takes some proof. If you're familiar with the Ehrenfreund game, one can prove it using that, but I don't want to get too far afield. I just want to state that if you have a tree and you have a node and you look at its children, and if you know the state, in particular the Ehrenfreund, this is called the Ehrenfreund class. So I'll just state as a logic fact that if you have a node and it has a set of children and you know the Ehrenfreund class for each of the children, that is to say for the tree starting with that child, then from that the Ehrenfreund class of the original node is determined. And furthermore, if there are k or more nodes of a particular type, it doesn't matter how many there are. It doesn't matter how many there are. So similar to the situation over here. And I said, if you're familiar with the Ehrenfreund game, this can be proven using the Ehrenfreund game, or it can be proven using some basic logic things, though I don't know how to do that. But I'm just going to take this as a fact. So just, since we're taking it as a fact, let me just repeat this, that so the state of a tree is really how it behaves with respect to all quantifier depth case statements. Okay, and there are only a finite number of states. Now I'm saying that if you have a point and maybe it has 53 children, there's no probability here. And for each child, you know the state of its tree. You know for each first order statement of quantifier depth up to k, you know whether it's true or not on that tree. And furthermore, that if k or more nodes have the same state, all you need to know is that there are at least, you don't need to know how many there are. Then the state of the original tree is determined. So that is to say, something like this will occur. There'll be some determination, which will be a little more complicated to describe, that goes from, so here what you have is number of green, number of blue, number of yellow. If the number of green is omega, no, if the number of green is 1, the counting is 0, 1, or omega, omega meaning greater than or equal to 2. If the number of green is 1 or omega, then you're green. If the number of blue is 1, the number of green is 0, the number of red is 0, then you're green. If the number of green is 0, number of blue is 0, number of red is 1, then you're blue. Everything else is red. There will be a similar thing for the Ehrenfreund class. Okay, so that, I'm not giving the proof, but it comes out of the logic. So now, yeah, question?
Is every first order property just given by the existence of a subtree?
Sorry?
Is every first order property just given by the existence of a certain subtree, like in your example?
No, that's not really true. I mean, these are existential statements. You can make more. You can say, for all x, there exists a y, such that for all z, there exists a w. You can make, I mean, you could say that if every time, you could say that every time a child and a grandchild had exactly 7 children, then all 7 of the...
Sounds like you're describing a subtree when you do that.
Well, there is a localness to it. It does depend on finite things. That's true, yeah. So in a certain sense, you're right. Yeah, there is a locality here that really is important. Okay. So now I want to get the solution as a fixed point, and so I'm going to define a map psi, depending on lambda, from distributions to distributions, and the solution is going to be the fixed point of this map psi. So the idea for psi is you have a distribution over the states, and now you take a point V, you give it Poisson lambda children, and then each child you give a state by means of this distribution. And you do them independently. Now you know the states of all the children. Therefore, you know you've determined, in this way that I've just stated, that's determined the state here. And if everything's going to work, we're going to have a fixed point. The solution is going to be the fixed point because, so this is a map from distributions to distributions. Once again, you're given any distribution over the states. You take a point, give it Poisson lambda children, give each child IID a state from this distribution. That induces the state of the parent. It's the distribution for the parent. And what happens is that the solution is the fixed point of psi. Again, I should write psi sub lambda. But what happens here, what we've been able to show, is that in the case of first order statements, that this psi has some nice properties. First of all, maybe most important, the fixed point is unique. So unlike the situation that I erased, where you have two solutions, there's going to be a unique solution to the equation psi of x equals x. Secondly, if you think of psi as a map from the distribution space to the distribution space, it's a contraction. Okay? Points are getting closer together.
Which metric?
Now, if you take a high enough, if you allow yourself to take a high enough power, then the metric becomes irrelevant, because if it's contracting in the, say, the TV metric, then if you take a high enough power, it's really contracting in the TV metric, total variation metric, and therefore it's contracting in the L2.
But which metric is the most natural? Which is the one where you first...
Total variation. Total variation, yeah. Although for application, we really want the L2 metric, yeah. But we'll see the total variation metric is the natural one to look at. So the results are that there'll be a unique fixed point, and even further, I mean, what we actually prove is that the map psi is a contraction map. So in fact, then it has to have a unique fixed point. And so the solution will be given by the unique solution to a finite system of equations, and all the equations just have the variables and various powers of lambda and e to the minus lambda floating around. So they're nice functions, and from that one actually gets that from the contracting property, that the solution, so the results are that it's contracting. I think that's sort of the main result from which other things follow. It's a unique fixed point, and and it's a smooth function. That is, all of its derivatives exist. So it's not like the place where it's not differentiable. All the derivatives exist. In fact, it's even more. It's real analytic. In fact, it's even more because it is the solution to these equations. It's called an algebraic function, I guess is the word. So everything. So these are the results that things are very nice about it. Let me give you some idea of what's happening here, and bring up another definition that turns out to be important.
Yes, it's algebraic in lambda and e to the lambda. So there's two.
Right. Yeah, that's right.
It's
Well, that's right. Yeah. But these are smooth functions. Let me bring in another definition that I like. So remember that I said that we consider the Galton-Watson tree, that the underlying space is this countable sequence of IID Poisson mean lambda variables. So let me say that a property, or for that matter, function A is rapidly determined if, I want to reintroduce a notation of Knuth that unfortunately died away, but I think it's really a wonderful. I want to say fairly surely, which he introduced some decades ago. Fairly surely means that the chance that it doesn't happen drops exponentially. Okay, so let me just introduce that for today. It never did catch on, but I think it's a very useful thing. So something occurs, you'll see there's an underlying parameter S. So something occurs fairly surely if the chance that it doesn't occur drops exponentially in S. If fairly surely x1 through xs, let me emphasize it by writing tautologically determine are either the veracity of the property or the, maybe it's a function. In fact, the actual thing is we're going to look at the Ehrenfeucht value. Let me give an example of something that's not rapidly determined, whether or not the tree is infinite. So consider the property that the tree is infinite, and think of lambda greater than 1. If you have x1 through xs with a positive probability, I mean bounded away from 0, at the end of x1 through xs, you're going to have this huge number of nodes that you know you have, but you don't tautologically know that the tree is going to be infinite. You know it's highly likely that the tree will be infinite starting from there, but you don't tautologically know. So being infinite is not rapidly determined, at least when lambda is greater than 1. So you're fairly sure that you're fairly sure, but you're not fairly sure that you're tautologically sure, and that's the difference. And the claim is that sigma, depending on k, is rapidly determined. Now, I don't want to give the whole argument. Let me give the argument for this particular statement. So look at the statement that there's a node that has exactly one child that has exactly one. Notice that that doesn't have limiting probability 0 or 1. It's somewhere in the middle. But I want to claim that it's rapidly determined. Okay, so let's fix x1 through xs. Now, the way I want to examine this is I want to use fictitious continuation. So what I want to say, so we're just going to look at this statement. In fictitious continuation, I want to use the x's to generate not just a tree, but if the tree dies, I'm going to start another tree. I won't call it the root anymore, but I'll just start another one. So let's define a new process based on the xi's that will use all the xi's. We just go along, but whenever something dies, we just start with a new node. So maybe we start out, suppose we started out 3, 0, 0, 3, 0, 0, 0, 2. The first node would have 3, the next would have 0, the next would have 0, the next would have 0. But then instead of the process stopping, so this is the root, I'll add a new vertex that has 2, and I'll keep on going. Now, I claim that fairly surely in this structure, there's going to be a node that has exactly one child that has exactly one child. So this structure is not ever going to stop. So I'm going to take it out to S, and I claim that there's going to be, and by that I mean that it's already determined by time S, so that there's a node that's had exactly one child, that's had exactly one child. But furthermore, the grandchild's children, sorry, we don't, yeah, no, that's all we need. That's all we need. So why is that? Well, there are a number of ways of proving it. I like to prove it using Martingales. We let I sub I equal 1 if I has exactly one child, which has exactly one child, and we're going to let y be the sum of I sub I for I less than or equal to epsilon s. Here's a little technical part. We don't want to go up to s because if we look at the point s, x1 through xs haven't yet determined they've determined how many children S has, but if S has one child, we don't know yet whether that child has had one child. But if we stop at epsilon S, where we pick epsilon, it'll depend on lambda, if we pick epsilon small, then fairly surely by the time when we get up to epsilon S, not only, so if we only look at the nodes up to epsilon S, all of their children and all of their children have already been determined. So that you can show. So I only want to go up to epsilon s, and I look at this, and now I say that the expected value of y is some constant times epsilon s, because each node, the probability that it has exactly one child, the kappa is lambda e to the minus lambda squared. It has to have exactly one child, lambda e to the minus lambda. That one has to have exactly one child, lambda e to the minus lambda. So the expected value of y is kappa times es. And now I want a large deviation result. I really want to say that y is probability that y is 0 is exponentially small. But I can run a Martingale on y. So I think it's pretty much required that the word Martingale comes up in any of these talks. So we run a Martingale on y. Where we look at the expectation of y as we look at x1, x2, x3, etc. what can be the effect of xi, so yi is the expected value, I shouldn't use I, yt is the expected value of y given x1 through xt. And now I want to look at how our expected value changes when we say how many children child t, the tth child, has. Well, that can affect whether t has exactly one child that has exactly one child. It can also affect whether the parent of t has exactly one child, which has exactly one child, but it can't affect anything else. And this is a tautological thing. Knowing how many children the tth child has can only affect the t itself and the parent of t. So what happens is you have a martingale. Each additional piece of information can affect things by at most a constant. In this case, the constant is 2. Therefore, you can apply a Zuma's inequality. So you have a large deviation, and you actually say that, so the probability that y is 0 is exponentially small. In fact, actually, the probability that y differs from this by constant s is exponentially small. I don't know that we actually, in some later things, we might use that. That might be useful, but I don't think we'll get to that. Okay. So now what does this mean? Does this mean that the probability of the event is going to 1? No, because this was with fictitious continuation. So now what you say is when you look at x1 through xs, in the fictitious continuation, fairly surely this has occurred. Now, what's happened is either the process has stopped by x1 through xs, but then we know whether we just look at the tree, see whether it's true or not. So then we absolutely tautologically know whether there was a node that had exactly one child that had exactly one child, or the process hadn't stopped by xs, but then if it hasn't stopped by xs, then the fictional continuation is what actually did happen. And so therefore, in that case, fairly surely it did occur. So we either absolutely know it, or we're fairly sure we know the answer. Putting them together, we're fairly sure that we know the answer. So what happens is, so I've just done it with this statement, but it turns out it works more general, that these statements are rapidly determined. And I think somehow that this is a critical property. If we want to move away from the logic, this is the meta property that we want to look at for the properties that it's, or at least one of them, that it's there. Let me just say a couple of words about the contraction. I'll just do the easy case where lambda is less than 1 and why this is a contracting map then, but I'm not going to give the whole argument. So with lambda less than 1, which is actually, I mean, there are a lot of ways there, the tree is going to be finite anyway, but still, I want to say that when lambda is less than 1, that if you use the total variational distance, then you're contracting. So the idea is take a node and let's condition on it having t children. And on the one hand, so you have two distributions on the state space, x and y, that have total variational distance epsilon between them. Epsilon does not have to be small in this case, epsilon between them. And so conditioning on it having, say, 4 children, and suppose that the total variational distance between x and y is epsilon. Now we couple the two. We give each node here IID x, and then we couple it with giving y over here. And what's the chance that the state up here is different? Well, if in the coupling we wound up giving exactly the same thing to all four, then they'd have to be the same. But each one, because of the coupling, only has probability epsilon of getting a different thing. And so even just taking their sum, the chance that you would get a different thing for, so in this case,
So since the case of lambda less than 1 is so obvious, maybe you can remark on the other cases.
okay,
Time.
yeah, okay, all right. Let me just finish this one up there just for a moment, and then I'll remark on the other one. Yeah, so here it's just lambda epsilon. Sorry, it's 4 epsilon, but 4 has an expected value of lambda, and so it's there. Now, what happens in the when lambda is greater than 1? I'll remark on the. What happens then is it's more complicated. You go down. So instead of psi, we're going to iterate psi, which means the following. We take a point, we go down s generations, and then at the s generation, we give all the nodes from distribution x, and then we backtrack all the way up and get the original thing. So I'm going to take s to be s naught plus n. First, I'm going to choose s so big that by the time we get down to here, the chance that we're not determined already is exponentially small. So let me just say it's less than epsilon 1. So before I said, now notice before I was looking at nodes one at a time, here I'm going down s generations, but that's even more than one at a time. So what happens is it's only with probability epsilon that the x is going to have any effect at all. Otherwise we're, but that's not enough for contracting because that epsilon is fixed and maybe x and y are really, really close. So now we say suppose that the number of vertices down at level s is t, and we don't have anything about what t is going to be. Okay, but what we want to say is this: if t is small, then the contracting argument is going to work because these t are going to give t times lambda to the n children, so that would give an extra factor of t lambda to the n, but we have a factor of epsilon that is going to have any effect at all, and so would be okay. The problem is, what if t is large? What if t is large? What happens then? Well, what happens then is we go down another n levels. So you can take n to be like 4 to the k, but that's the technical part. These are independent trees. If inside of these trees every type occurs, and every type occurs at least k times, then everything will be determined by here. Okay, again, that follows from that. That's one of the logic parts of the argument. That is, if every kind of tree occurs inside here of a fixed size and occurs at least k times, then everything will be determined. And the chance that that won't happen is exponentially small in t. So the chance that it's, so call it bad, if it's not determined, the probability that it's bad is exponentially small in t. When it is bad, we're getting an extra t times lambda to the n, which is hitting us on the contracting is becoming expanding, but it's t times lambda to the n, but times e to the minus beta t. So when t is big, the e to the minus beta t is going to cancel the t. So when t is very large, what happens is, again, it's just contracted. So this is an outline of what's the most complex part of the argument that that shows that indeed it is contracting. And you don't need the contracting to show the unique fixed point, but you do need it to show that the function is real analytic. So let me mention some other possible things to think about here. One thing is, if you have a recursive property, does the recursive property uniquely determine, or maybe uniquely determine up to probability 0, the event? So if you think of that, if you have a green child, you're green, okay? I use that for being infinite. But there's another model with that same rules for green and red. Just call every node red, no matter what it is. Just call it red. Then it's going to have the property that if you have a green child, you're green. And yet the probability that you're green is going to be 0. In fact, that's the spurious solution. So what happens is, when you have the rules for the recursive function, they may not determine uniquely the property. And indeed, that's actually the case for having a single child that has a single child, because then again, do the green, blue, and red, except now say that if a point has an infinite tree below it, just call it green. Don't look, just call it green. Well, that'll still have the property that if it's green, it's green. See, if you have a finite tree, then the leaves are determined because they have no children. So their state is determined, and then you can backtrack. So when you have a finite tree, everything's determined. But if you have an infinite tree, parts are not determined. So in the case of having a single child with a single child, there also is a second solution, but that second solution has the same probability, because when you do have an infinite tree, you're going to have the property. So there's some connection here with what about the uniqueness, or uniqueness up to probability 0 of recursive properties. There are questions about, all right, here I started out with this from the logic point of view, but what if you just start with assumptions like rapidly mixing, or maybe something stronger or weaker? Can that by itself tell you some things about the property? Always the goal is to say something nice about this function, is to say something nice about, or to say that there isn't. There are cases where it's not nice about it. And let me add one final question that I've been puzzling over and haven't done. As was pointed out, this model has locality. I mean, basically, these first-order statements are, you're really kind of talking about local neighborhoods in some way. So I can destroy that and keep a first-order language. I can add a first-order binary predicate that X is an ancestor of Y. If I add that predicate, I still have a first-order language. It still has the property that there are a finite number of Ehrenfeucht classes. So you still get everything as before, except that you don't. I certainly can't get these results, and I'm not even sure that these results hold. So one question is, can you come up with a sentence involving ancestor where the function f of lambda is not a nice function? And I think that's a good point to stop. Thank you.
Comments or questions? So maybe one comment you already made in Sweden was the one that two verses in the same level is a problematic element if you were to add that to your language.
The problem is that if you put in that binary statement, you can actually say that the tree is infinite, because then you could say that for all x there exists a y at the same level that has a child. So this logic business is a tricky thing. You know, you keep thinking, well, let's strengthen the language, and sometimes very quickly you strengthen the language, and you know, you just get, you know, you get stuff that you don't want. Ancestor, I'm just not sure. So that's why I'm pulling back a little bit, thinking about ancestor.
So you don't have the contracting property in the ancestor case.
Sorry?
So contracting property doesn't work in the ancestor?
I don't know. I don't know. My guess is that certainly the proof doesn't work,
Right.
because all the proofs serve as it seemed like your insight was that there's a locality to what's going on, and in a certain sense that permeates all the arguments that you can look at. If the notion is that, so just notice, if you have a tree, well, there's the neighborhood of the root. You have to know about that. I mean, after all, I mean, you can make statements that the root has 5 children because the root's a constant. So there's the neighborhood of a root. But otherwise, if you've got, fixing the quantifier depth k, if you've got sort of for each of a finite number of classes, you have k copies of sort of sub-trees or bushes that look like that, then the Ehrenfreud value is determined. That and what's happening near the root. So in particular for infinite trees, when conditioning on the tree being infinite, you've got every possible local configuration. And so what happens is the theory really, if you condition on being infinite, it collapses in a nice way that the probability, for any statement A, you only look at what's happening locally near the root. And how far down from the root just depends on the quantifier depth of A. And if you know that, then you know whether it's going to be true or false up to probability 0. So, yeah.
Okay, so let's thank Joel again.
Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.